Here is a paper titled Efficient Estimation of Word Representations in Vector Space. Let's talk about it. Given this paper came out in 2013, I'm curious to learn more about its lasting impact.
Well, this paper is often cited as being influential in the field of natural language processing, NLP. The methods proposed in the paper made a big difference in how we represent words as vectors. It is definitely a relevant paper that seems to have had an impact on a lot of subsequent work.
I see that this paper is focused on efficiency and scalability, which makes sense given the context of big data and increasing computational power at the time. Can you elaborate on why that was important and perhaps what some of the limitations were with previous approaches?
Absolutely. See, before this paper came out, most NLP models treated words like individual units without any connection to each other. This approach had its advantages, like simplicity, but it didn't capture the relationships between words, which limited the effectiveness of models on tasks that required a deeper understanding of language, such as machine translation or question answering. There were some attempts to capture these relationships, but they were often too computationally expensive to scale to larger datasets or vocabularies.
Right, I just see the authors mention LSA, latent semantic analysis, specifically as being one such method that had scaling issues. I'm curious, though, how did this paper address those challenges to improve both the efficiency and accuracy of word vector representations?
The key insight of this paper was to simplify the neural network architectures used for learning word vectors. By dropping the nonlinear hidden layer from neural network language models, they created two new log linear models known as continuous bag of words, SIBO, and continuous skip-gram. These models were not only simpler, but could also be trained on much larger data sets due to the reduced computational complexity. This meant they could learn more accurate word representations with less computational cost, which was a big deal.
I'm seeing SIBO described as predicting the current word based on its context, while skipgram does the opposite. Can you explain why the authors introduced two separate model architectures and if they had different strengths and weaknesses?
That's a great question. You see, the paper presents these two architectures as different approaches for learning word relationships. SIBO is kind of like learning by looking at the surrounding words and trying to figure out the missing piece of the puzzle. Skipgram, on the other hand, is like learning by giving a word and then trying to guess the words that are likely to appear around it. These are complementary ways of learning language, so each model learns slightly different relationships.
The results section mentions a word offset technique, which sounds quite interesting. It almost sounds like word vectors are being treated like mathematical objects. Is that the case? And how does that work in practice?
You're spot on, it's fascinating. The paper demonstrates that these word vectors exhibit linear relationships. For instance, vector king minus vector man plus vector woman results in a vector that is close to vector queen. These linear relationships reflect the semantic and syntactic relationships between the words. The paper discusses a new test set for evaluating word relationships, which includes evaluating word embeddings beyond simple similarity tasks.
That is fascinating. It's impressive how these linear relationships can capture different aspects of a word's meaning and how it relates to other words. This must have had significant implications for the development of downstream NLP tasks, right?
Exactly. And the paper has inspired a lot of subsequent research into the properties of word vectors and how they can be used to represent not just individual words, but also phrases and even concepts.
Regarding the results, the paper mentions training on a massive data set of 6 billion tokens from Google News with a vocabulary of 1 million words. At the time, were these considered large-scale experiments, and did they demonstrate the effectiveness of the proposed methods in comparison to previous work?
Yes, these were definitely considered large-scale experiments at that time, and the paper shows they led to significant improvements over the existing state of the art, not only in terms of accuracy, but also training speed.
The paper mentions a distributed framework called disbelief that enabled parallel training of models. Can you explain how distributed training accelerated the process of learning word vectors and made it possible to handle such large data sets?
Distributing the training across multiple machines allowed these models to learn from much more data in a reasonable amount of time. The paper shows how, with disbelief, the researchers could use 50 to 100 or more model replicas, which significantly reduced training time, even with larger word vector sizes. For example, training the skipgram model with 1,000 dimensional vectors took 2.5 days on 125 cores, as reported in the paper.
And that's all for now. Thanks for this insightful discussion.